Okay. Yes, you can
Yes.
start now.
Okay, so today we'll be talking about patterns in mathematics, but by this I don't mean a pattern that comes one time, but a pattern that is in its most general form. It repeats all over mathematics. So yes, I have thought of a few examples. So yes, I think we should start with the simplest pattern and see how far we can generalize it. Okay, so I think here, okay, oh no, yeah. So the simplest part I could think of is addition and multiplication, but not in the sense that if you add two numbers, you get another number and so on and so on. I mean, we can see addition and multiplication in several different ways, all where it means different things. After all, for if we just look at natural numbers, then addition and multiplication is quite simple. And then we can also have addition and multiplication in various other things, matrices. uh, Then we also have modular arithmetic, where if you add anything to itself enough times, then it goes to zero, which is also not there in our usual addition and multiplication. So, what is the most general form we can think of, which still has these same four properties? So, that's what we'll be thinking of. So, first, we would like to have a simplest example, much simpler than just natural numbers, integers, even simpler. So, does anyone have an idea for a very simple one? So, just a moment to think. Yeah, maybe it'll be more clear if I give a few examples. So, this is certainly the simplest I could think of is what if we consider or and, because we can see it's sort of like multiplication. All these formulas about A and B union C is, so it is sort of like that. But which of these is more like addition and which is more like multiplication?
Or is more like addition and is more like multiplication.
Yes, in fact, usually we will think of them this way because we have a clear eye. But in fact, if you look at it very closely, there is actually no difference. So if we swap yes and no, usually in yes will mean yes and no will mean no. But if we just treat them as symbols, or and are the same. But usually, yes, or is treated more like addition and is treated more like multiplication. But if we swap yes and no here, we get this. So, yes and yes, which is just no and no, is yes, which means no. So then that is that, and yes, it turns out to be the same. But usually we will think of this as plus and this as multiplication. So we can also generalize this in an interesting way. If we just do this several times, somehow we can generalize this. Yeah, I accidentally, yeah, it's the So if we look at it for several things, we can have some yes and no's. So we have four things. If we just call the yeses as ones and the no's as zeros, we have 0, comma 0, 1, 0, comma 1, 1, comma 0, and 1, comma 1. And then OR is just 0, comma 0 with any of these. We just do the bitwise OR. But then this is for two elements, two different ones. If we do the same thing for a set, and we take the associated subset as all elements where we associate a 1 with them, then it just becomes into union and intersection. So yes, similar things do hold for these also. So, and then we also have normal addition. And all of these do behave a bit differently, but underlyingly the thing is, yeah, just pretty much the same. So now I guess I take some questions. So otherwise, can we think of any more examples which are sort of like addition and multiplication, but it's very slightly different. So we can call it as addition and multiplication. Yeah, at the very beginning, I had said a couple of examples which behave more differently, but we still use the same addition and multiplication for both modular arithmetic and matrices. So, since we don't seem to have any more examples, I guess we can now look at the common properties. So, does anyone want to see some common properties that these have? All of them.
Commutativity.
I think Mandar said commutativity, right?
Yes.
Yeah.
So, yes, we have commutativity of addition in all of these. And yeah, we also have
Associativity.
commutativity of multiplication. Yes, associativity.
But like, matrix multiplication is not commutative, right?
Yes, I was trying to check. Yeah, even though this is true for most of them, for matrices, which we did see as an example, it is not true. Yeah, you got me.
Could we go over the properties of matrices?
So if we look at matrix multiplication, it isn't commutative because we can have a 1 by 2 matrix and wait, yeah. Oh no, I forgot. Is it? Ah, wait, just a second, sorry. Yes, so we have two matrices like this, and then we multiply them by looking at the rows and products. So we have this 1 and 1. So then we end up with the matrix of 1, 2, 3, and 2, 4, 6. But if we look the other way around, then it turns out that we can't multiply these at all because matrices are, well, this is basically matrices are supposed to be sort of a numerical form of linear transformations. That's why we have the multiplication by vectors and all. So from this is going to two dimensions. Wait. Okay, sorry, I might be getting a bit wrong here. Yes, yes. Sorry. Sorry. Yeah. Yeah, sorry, I got it confused. If you no, sorry, but
Wait, can I like 6 of my should I? Bairav,
y- yes,
do you want me to like tell the basis of my?
yes, thank you. Sorry, I got a bit carried away with the exam.
No, no, it's fine. See, so like essentially the idea is like a matrix is essentially just an m cross n array of stuff. Okay, like those are just numbers. There can be other stuff, but that's out of the point right now. So, when you are multiplying two matrices, the condition is that like this object here, let's say you have to multiply two matrices, which are a m cross n and a cross b. So the condition actually is that a has to equal n. This like these two have to be equal. That's condition. Because actually how matrix multiplication works is say you have some matrix uh one what and yeah. Say you have like one, a bunch of ones, and then you have another matrix which is a bunch of just two. So what you do is you take the first column over here and element wise multiply them by the first row over here, and that gives you the first row of your uh, resultant matrix. So does that make sense? Don't
Yeah.
yes. So like do you
So
see
we
why
could
we
start
need
with we would get something like this, right? Like for
yeah
the beginning, three, exactly three, or should there be more?
yeah no no, like that depends on how large your matrix is. But do you see why we need like the number of columns here equal to the number of rows here? Because we are multiplying them element wise, right? So the elements here should equal the number of elements here. Does that make sense?
Yeah.
Yeah.
Hmm.
So this is the reason why matrix multiplication is not commutative. Because see, if m is equal to a, n is equal to a, then we can multiply it like m cross n multiplied by a cross b. But for it to happen the other way as well, m has to equal b.
Right, right, yeah.
Yeah, so that's the reason it's not where I can't delete
Yes,
this stuff for you. Yeah, fine.
yes, thank you, thank you. I got a bit confused.
I don't think I can erase the stuff Rohit has written to the same.
No, you have erased.
Ah, thank you.
No, yes, sorry. So yes, these are the simple things. Mm, there are some other famous ones about multiplication and addition, such as Yes.
भैरव
Well,
भी कर सकता हूँ।
okay, yes. So I guess now I'll just tell you the rest. So yep, these are the common properties out of all of these. Sorry for this transitivity. I made a mistake. It should have been distributivity. I forgot the name. Yep. So these are all the common properties. And you can see identity seems a bit obvious, but you can have stuff where you can have addition, multiplication, and no zeros, no ones. Yeah.
And like as we saw commutativity, I don't think is one.
What?
Like commutativity is not one of the common properties because matrix multiplication.
Yes, well, commutativity of addition is there.
I think we're talking about addition and multiplication now, right? Just those two.
Yeah. No, we're
Yes.
talking only about addition because multiplication. Commutativity doesn't work. Mhm.
Okay. So, yep. Commutativity, yes, you already found it's not there. Not there is, it doesn't work for text. But if we look at inverse, it isn't there. See, we can have 2, which is an integer. Half is not an integer. 1 is a natural number, and -1 is not a natural number. By the way, for the identity, I am taking natural numbers to be non-negative integers. Yes, so these seem to be the things. But is there any way we can add more properties by just doing a simple trick? Because after all, how did we get to integers? We got it by adding negative numbers, right?
Mhm.
So maybe we can do the same thing here. We can add negative numbers and then we also have additive inverse. But
What about
unfortunately,
multiplication then?
Add reciprocal.
multiplication is also quite interesting that you can do.
Yes. For that we add non-zero reciprocal. Right? Wait, am I not audible?
Yes, you are.
Am I audible?
Yes.
You're audible, it's just a bit low volume, that's the only thing.
Yeah.
Uh, so I was saying to like get the inverses for multiplication, you add in all the uh, inverses.
Yes, you can do that. Then you also need to be a bit careful defining all the fractions.
Yes.
So yes,
Exactly,
that
that's the problem.
no, that can be done usually. But if you have zero divisors, it becomes a bit more complicated and so on. But you can usually do it.
Yes.
But you additive inverse seems like it would be easier after all. Since you just get negative one from one. But it turns out that it isn't always that easy. Yes. So if we go back to our very first example, and yes, we'll just call or as plus, this is times, yes is 1, 0 is no. So suppose we have a -1 here, but then 1 plus -1, this will be 0. But if we look at this table closely, we see 1 plus 1 is equal to 1, which leads to an issue here. So now we can just write 1 plus 1 plus minus 1 by this, by the associativity, and then we get 1 plus 0, which is 1. So yes, so if we try to add additive inverses, we get that 0 is equal to 1. And so we get a table of, there is only one thing which is 0, and 0 plus 0 equals 0, 0 times 0 equals 0. And this sort of thing can happen if we try and add multiplicative inverses as well. But for the sake of time, I guess I won't be taking that. But you can get some interesting things if you try and add fractions. If you take mod 6, then add fractions to those, you actually get mod 2, which is smaller than it. Because for mod 6, we have 0, 1, 2, 3, 4, and 5. And then when we add all the fractions, if we do it properly, we get just two different things. And if we consider those as 0 and 3, those don't work. If we consider just, then it becomes somehow smaller. Yes, so that brings us to the definition of all these axioms, which usually occur, but notice for distributivity we have two different axioms because commutativity of multiplication is not guaranteed. And yes, this additive inverse axiom isn't there for a few sets. For natural numbers, we can add it, and so for most of these addition and multiplications that we will consider, that people consider, this property is there, but in a few it isn't. So when it has all of these properties, we call it a semi-ring. If it does have this one too, we call it a full ring. And then you'll notice some of our examples have another things, such as if we take rational numbers, real numbers, complex numbers, then all of these are having multiplicative inverse for all non-zero elements as well.
Yes.
So
Bhairav, yes. In the chat, they're asking what has been like. I think Sharayla joined a little late. So could
Yeah,
you just
sorry, I
please?
joined a bit late. Forgot the class.
okay. So what we were discussing was what we usually have as addition and multiplication. So not just a specific case, but we have many things as addition and multiplication. Addition and multiplication of integers is different from modular arithmetic addition and multiplication, which is different from matrices addition and multiplication. So we are considering what are the common things. So by considering those, we've arrived at all these axioms, which are in common pretty much.
Ah, okay. Wait, so ring axioms are for what?
For most of our cases, it will be a ring. So integers are a ring because all of these are most of these properties hold usually. And this is just this sort of stuff. And most of them hold wherever we can call it addition and multiplication, but sometimes additive inverse doesn't hold. So if that is not holding, we call it a semi ring. Otherwise, we call it a full ring. So this is just a structure so that we can check some properties of it. And so, in fact, there is a quite a nice way to have the two sets, and then we have addition and multiplication of those two sets in quite a nice way. In fact, we take the symmetric difference, and this is just the intersection. And in this case, we in fact see that this is a field. In fact, so we do have a bit of a work, I guess.
Bairav, could you go over what a field is?
Okay, so a field is basically the same thing, but we have commutativity and multiplication and multiplicative inverse for non-zero elements, because we also have these sort of things which do have all these, so we can add some extra constraints upon them.
Okay, thank you.
So we have this also this one interesting thing. You can define addition and multiplication on arbitrary sets, which are all subsets of the same set. Um, but if you make it for all sets, which I guess you can, since you take multiplication as all elements in the as the set of the intersection, and we take addition as all the elements which are in exactly one of them. Or just A union B minus the intersection, and you can check almost all of these axioms are satisfied, I think. But just a second, sorry. If we look at additive inverse, we can actually take A plus A is just A minus A, which is the empty set. But what do we take as 1 exactly? So that will have the property that A union, no, sorry, A intersection B is equal to B, which would mean that B is equal to the empty set. But then again, if we look at it, the empty set is also 0, the additive identity. So yes, it is a
So
bit
are A and
strange.
B two arbitrary sets?
Yes.
Then, if they are arbitrary, then in the last line of their A intersection B is equal to B, could it be that B is a subset of A?
Yes, but since A is arbitrary, well, in this case, B will call it as, well, 1.
So B is just a one element set which has just one.
Yes. No, no, as in we'll call it as 1, even if it isn't a set which only contains 1, or we'll call it E. So this means that A union E is equal to E for every set A. And we'll call it the identity since we are defining multiplication as union.
Okay, so for every set A, all right.
Yes. Well, actually, sorry. If A intersection E is equal to A for every set A, then this set would have all the elements. So it would change. So it might not be considered a set. So that's something to for you to think about. This has all the axioms satisfied except for the ones which involve the multiplicative identity element. So those are not there. So yeah, these are quite interesting things. I guess we can take a break here.
Right.
Yes, this is a bit of an introduction to these. Hopefully, you get interested. Sorry, yeah, if I made some mistakes and such. So yeah, this was an introduction. Hopefully, you get to know more about these are quite interesting. Yeah. Then I'll do a short example. So Diophantine equations. So we'll have a interesting Diophantine equation which squares are triangles, and then we'll see how it's connected to these. So of course, if we simplify it, we get this. And since these are co-prime, we can get that one of these is a square, one of these is twice a square. Because every prime number other than 2 has to be divisible. Every prime number has to be divisible by exactly one of these. And all of them have an even power divided by n square, of course. So then we get that one is 2 times a square and the other is a square because of this 2. And we get Bell's equation. But usually we would solve this by doing some strange sort of x plus yeah x prime plus 2y prime minus xy prime and such, and we will do that, but we can find something interesting if we just are willing to look at the square root of 2. And so it turns out that all these strange forms of multiplication that are being done here are in fact just multiplying the these parts because It's just the same thing you would do if you do this. So then these would be invertible, and so we can actually see some theorems from the rings and fields which can help us with this. So yes, we can apply something quite abstract and yet uh, some solutions for a Diophantine equation. Yeah. So are there any questions?
No, not yet.
Okay. So we can also do the same thing for anything, and we can simply prove the two prime theorem if we assume some things about the Gaussian integers, in fact. So maybe should we do that proof now? Yes.
Yeah, we can go over Gaussian integers,
Yeah,
like what they
so,
are and how they get used to this.
Wait,
so
what are Gaussian integers? I don't know.
yes, yeah, just if we take I to be the square root of -1, abstractly, then we just define this x plus yi plus, where both of these are integers as Gaussian integers. So to prove the two square theorem, if we will just look at a prime which is congruent to 1 mod 4 and show that it's the sum of two squares. Yeah, so in fact, since it is 1 mod 4, we have quite an interesting thing. We can take p minus 1 by 2 factorial. So this is 1 all the way to p minus 1 by 2. And then this is p minus. So since we are taking this mod p, this is just minus p 1 by 2 times until -1. And since p is 1 mod 4, this is an even number. So then this is the same. It's just this twice. And if this would be the same as p minus 1 factorial mod p, but this is congruent to -1 by Wilson's theorem. So we get p minus 1 by 2 factorial squared plus 1 is equal to AP for some multiple A of P. So we get, so then we can just factor this with Gaussian integers. And then we use something interesting, which is that in Gaussian integers, just like uh, in integers, we have unique factorization into primes. which is not necessary in fact, because we can have, if we take arbitrary things, we can, instead of taking the square root of -1, we can take the square root of -5 and just have 6 is equal to 2 times 3 and 1 plus root of -5 times 1 minus root of -5, and this is 1 minus -5, which is 6. So it isn't necessarily there, but in this case it is there, which in fact allows us to factor this and this both into primes in the Gaussian integers. But since these are conjugates, we can also get the primes will be conjugates themselves. So we get this as AP, but how many of these? So we can actually include these into other things. So we get, say, Q1. We just get a prime factorization of AP. We can't be sure these are primes yet, but so at more one of these has to be a P, and since that is two of these, and so this must be a 1 since it's a prime. So we get that P1 times P1 bar is P. But what is this P1? It will be some N plus Mi. And P bar is N minus Mi is P. So we get that it's the sum of two squares. And it's it's a much simpler proof.
Yeah.
Okay, so I guess we can look at the next subject topic.
Okay, that's good.
So it's about functions. So we first look at bijections, which are an interesting type of functions, and they have inverses. So then, in fact, the condition we say that they have the same cardinality if and only if they have a bijection between them. Because we can see for finite cases, if there are 3 and 4 of them. Sorry, what is this? So if we can see there are 3 and 4, there has to be one which is not in the image of this function. And if there are less on this side, there has to be one which is covered twice. So we can't have an inverse here, we can't have an inverse here. So it is a bit boring if we have it as a set, because then it'll just be the same as any other set now. So we'll just take a small special case where the both sets are the same, and then we can see that these are the examples. And yeah, oh no, I put the table already. Yes, so these are all the permutations of three elements. And I have labeled them like this, where one is the fixed point of this, and two is the fixed point of this, and these are two cycles.
How did you get these cycles? Like, what do you mean? Okay, I see a bijection will have two sets. Then how do we get this?
Yeah, so we'll just take the special case where both sets are equal.
Mm-hmm.
Yep, so in this case, we can just look at the ones here and we see some nice properties. So we basically get a group definition, which is pretty much the same properties we see here. And the inverse is because we have a bijection. Otherwise, we could not have this, and that would be some issues in the later ones, I guess. Just wanted to share a nice theorem, which is that if we have any finite group which has the same properties as this, basically, we can find some n where it will be fitting in the permutation group of n elements.
What is a SN? Again, like every finite group is in an SN you wrote. So what's
Yes,
SN?
yes, it's just the symmetry of n objects. So here we have all this with multiplication as S3, and this is S1, S2. So that's what we call as Sn. So amazingly, we can have this theorem, which is that every group is in one of these. Yeah. So the proof is equally amazing.
Mm-hmm.
It's quite nice. So we turn the elements of that group into permutations of the group. So we just, if we have, oops, if we have a group, we just take the permutation of elements which is taken by multiplication by that element. So then we associate it with that and then we get a function. See, if we take a group where we have three elements, 1 c and c squared, where the multiplication is like this. So here it's pretty much the same as addition modulo 3. So we can see we get if we look at each row, we get a permutation of these elements, which from this element we get the permutation. And so we just take that function, and that in fact gives you the same group, but inside a permutation loop.
How did c times c square, how do we get that as 1?
Well, because this is just the structure of the group. It's the same as addition modulo 3. So,
Okay, so we're going with mod 3.
yeah,
Or is it similar to it? Are we using it or is it similar to it?
it's just the same, pretty much.
Right.
So, when we take, for example, the element 1, we take, then we get the elements of this group. So, 0 goes to 1 goes to 2, and 2 goes to 0. And if we just renumber these as 1, 2, and 3, we can see this is one of these. So we sort of get C1 and C2 from C1 and 2 here. And then you can see, because we just take the identity, in this case 0, and that always goes to that element. So no two of the elements in the group ever make the same one. And this function is injective, and it's also multiplicative, because if we also take the other one, which is the which we get from the element 2, and then we add them, which gives 0, would be the same as us composing these two functions. So we get 0 to 1 to 0, and then 1 to 1, 2 to 1, and we get the same thing as we would have taken by taking this identity element. So
I
it
see.
preserves the structure, and we basically get the same thing inside it. So now I guess we're done with bijections. So we'll go to involutions. So it's a function which is its own inverse. And many of these were not. But in fact, any involution is a bijection, because it is its own inverse, implies that it has an inverse.
Right. So
Now,
it maps to itself.
no, no, as in it is its own inverse as a function.
Right. Like when you map the element to its to an inverse, okay, they might. So if when you map an element of that set to its inverse, you get the set itself. That's what I meant.
Yes, that does work for groups. So if we look at a group, we do get that if we take the function of every element in that to its inverse, that would be an involution. But in this context, we're going to just look at general involutions. And we can also look at involutory linear transformations. So, a linear transformation means that if we have any multiplication, it passes out, and the addition passes out. So, what about a simple case? We have it from real numbers to real numbers. Then we get f of x is just f of 1. So then these are pretty simple. What if we have a bit more complex ones? So here again we have the same thing, only the output is a vector. So we just get xa, xb. It's the same thing. So what if we get a larger example? If we take from the plane to the plane,
So isn't the square of all the real numbers just the real number set again?
oh no, sorry, not. I didn't mean like that. I meant like it isn't square with respect to that. No, these are the sets itself. Sorry, I didn't mean like that. I meant R squared as in R cross R, which is just the set of all pairs of real numbers. So two-dimensional vectors. I think you're muted. Could you please unmute and ask your question?
Oh, right. So I can't see a presentation. Could you represent once? Maybe it would turned off.
Oh, okay. Now is it working?
No, I can't see it. Okay. I can't see it.
Wait, that's strange. Mm, Hmm. Yeah. Mhm.
Right now, yeah. Now I can see it.
Yeah.
Thank you. Right. So you said that R square is not the set of real numbers that are squared. So what are they?
So we would say that the Cartesian product, so it would be the set of all pairs of real numbers, which is just the same as with 2D vectors or points in the plane. Yeah. So here we could just say there are two units, not a normal basis. Yeah, no. So we just take our normal two vectors and then that we get two vectors from here. So now when we add this, we get that A1, A2, and this is just A1, maybe, yes. A1, D1, and this is A1, D2, A2, C1, and A2, C2. So we get this as the formula for our linear transformation, and we can also compose them to get other linear transformations. So, yeah, I already had this earlier just in case. So, it turns out that when we try and write them in this sort of form, so here if we write the coefficients, we can see it's actually turns out to be the same as matrix multiplication. So
Right.
this is actually how matrices are kind of coming from. Matrices, if we take an n cross n matrix, that is pretty much equivalent to a linear transformation from Rn to Rm. So let me take another one, an m cross k matrix, which then goes to Rk. So we can multiply matrices like this and we get a sensible result. Whereas the other way we get m to k, then n to m, which does not always need to make sense. But so if we use these usual basis vectors, then we can turn a linear transformation into a matrix, which is effectively how we get the matrix multiplication.
I see. Yeah, that looks cool.
Yes, so we can also look at some involutory linear transformations. So if we have them as 2 by 2 matrices, then we get this is equal to 0, this is equal to 0. This is just for a matrix squared, I guess. So when we divide these two, wait a second. Sorry, oh, wait, yeah. Sorry. So we get that C11 is minus C22. And also that C11 squared plus the product of these two is 1. So yeah, we can also look at involuntary linear transformations, but I also wanted to share some other nice uh, involuntary functions geometrically. So reflection about a line usually is just involuntary because we just reflect twice and we get back where we were. Reflection about a point is also the same. And it's another nice function. Inversion is also involutory if we look at everything other than the center of inversion, because these two have the same product even if we take them into different sides.
Yeah, the center doesn't make sense that way.
Yes. Yes, it doesn't. So I wanted to share a way in which inversion around a circle is sort of similar to reflection around a line. So to do that, we need stereographic projections, which comes quite interestingly. It isn't a projection in terms of the functions which we'll see, but it is a geometric projection. So we'll just say, what if C and D are the inverted versions of each other? Then then we use, because this is a right angle and all of these are. So if it's inverted around the circle A, with the center A and the radius is AB, then we get that triangle ACB is similar to triangle ABD. Then these are perpendiculars because these lie on the semicircle. So yeah, stereographic projection, by the way, is just we have this sphere and we take the top point of the sphere and draw lines through it from the sphere to the plane, and we project from the sphere point to the plane point.
Mhm.
So this in fact means that triangle A D prime B is similar to to B C prime A.
So all four of these triangles are similar.
Yes, just in different ways. And that gives an interesting thing because that means that this angle is the same as this angle, and we take the perpendicular bisector which goes through the sphere
So
because
they're
all,
reflections of each other over the perpendicular bisector.
yes. So if you look at it, it is reflection around this inversion around a circle which, which sort of goes around here is the same around as reflection across this plane. If you look at the full version,
Yeah.
but
Mhm.
yes, I thought it was interesting and just wanted to share it. So now we'll look at projections. So what it is that if we look at its range, it has to be fixed at range. So, for example, if we have, say, these four things, And then this goes to here, this goes to here, this goes to itself, this goes to itself. Say something like this. Then even though it looks like it should be identity, it could be that all of these go here to these points which are themselves fixed. So technically, these kinds of projections do follow that, but geometric projections really usually follow different rules. You only get this sort of thing by a bit of cheating and saying they're from the whole 3D space to a plane. Because usually we'll take them from a plane to a plane. So it's a bit odd. So there are, however, interesting things if we look at this sort of projection from very basic function. If we look at something here, the Chinese remainder theorem is actually a theorem about this sort of projection, in fact. So we have a bunch of prime powers, and we say that the modular congruence is just the same as all the modular congruences of the separate prime powers. So say if we had some sort of mod 12 and we sort of say it has a grid like this, where this is the mod 3 and mod 4, and this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is the mod 12. If you look at it, this is 1 mod 4, 2 mod 4, 3 mod 4, 0 mod 4. And this is
Right, yeah. And the other is one in 0, 1 and 2 more thing.
yes. So what the theorem is basically saying is that it will be the same if as long as these are relatively prime. This is basically a rectangle and it's uniquely determined by both its projections into here and here. But then again, but the relatively prime part is important so that you don't cross over
Right,
too
actually,
early.
yeah. Mhm.
So you can in fact get even more general versions of this. If you have primes, well, if you have different modes and you, but it's a bit more complicated. Well, so yeah, are there any questions?
No, seems perfectly clear.
Yeah, I guess we'll go to the extras. Then,
Yeah.
so suppose we have an infinite chessboard, which I'll model with a table. So here we go. Infinite chessboard. So we have a very special kind of knight. So suppose this knight is here. This knight cannot move here, but can move here. So the knight can go two steps in any direction and then one step no only anti-clockwise and not clockwise. So let's just put this knight in the center. So then this knight can go here or here. So the knight can go in all of these locations and none of the others, which is quite interesting, really. And what fraction of the positions can this knight go in?
So out of the eight positions that one knight can go, we now restricted it to four.
Yes.
Okay.
So your normal knight can actually go to any square because it can just go here, here, and then here, which moves it one step and then the same thing vertically. But this one can't go to all the squares.
Right, you can only go on these parallel lines alternatively.
Yes. So if I just get another pen color and use it to have a knight which is on a different starting square, we can see that this knight can go to all these places and such. So if we look at it, in fact, we can draw all these knights
So
and
we would need five knights to cover the whole board.
precisely. So yeah, we have these five knights who can cover the whole board. So even though we only have half the moves of this knight, we have in fact restricted its reach by 1/5.
Yeah, that's interesting. Hmm.
Yeah. And what's more interesting, we can restrict it in different ways to give it more or less freedom. So I'll get another infinite grid here. Second, I need to delete the old one. Get this one. And so, what if we have a new knight and this knight can go either here, 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 or here? It's still four different ones, but now
So you have
it's in,
restricted the ones that go vertically twice up or vertically twice down.
yes. So now the knight can only move like this. cannot
So
hit all.
this is not your regular 8 by 8 chessboard, right?
Yes, I put it 10 by 8, but it serves the purpose.
Right, because if it was 8 by 8, then we would have the last column having no possible places to go on the last column. If it was 8 by 8.
So if it was 8 by 8, these two would have been gone.
Right.
So here we can actually clearly see on half of these horizontal lines there are no places it can go. And then on the other ones, exactly half of the places it can go. So this has 1/4 of it. Whereas this right where the only difference is the angles between these.
Right.
And there's another one. So if they're so these four ones in the first one, they were all bunched up. Weren't they? They were no, they weren't bunched up. They were the opposite of bunched up, and they all were perpendicular, the different directions it could go in. In this one, they're a bit closer to each other. Here, 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 and here. There's another possibility where it's even more close together, and that night has even more rain. So this knight can go here, 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 or here.
So you kind of rotated what we had before a bit up.
No, actually, if you look at it, these angles are a bit different, very slightly.
Very slightly they are, yes.
Yeah, so here you can see the knights can move diagonally along one way. So in 1/3 of diagonals, they are there. And in the other bits, they are not. So this knight can move to exactly 1/3 of the places.
Right. So now we first had 1/5, then fourth, then a third now.
Yes.
Mhm.
So you can do similar things with other ones. But there is one thing where both of these are not symmetric. If you look at this, if you go right and left, you have a gap of 4 before meeting another place the knight can go. But here there's only a gap of 2. Here it's symmetrical across horizontal and vertical.
Mhm.
Diagonally, this one takes 3 and this one takes just 1. Whereas this one is very, very symmetric.
Yeah, you can kind of imagine it. Yeah.
Yes. So we can also have a generalized knight, which instead of going 2 and then 1, it goes A and then B.
So A and B are positions on the board.
Yes, A and B are this number and this number.
Okay. Yeah. Huh? Mm-hmm.
Okay, so now let me tell you something amazing. If we do this, it's actually equivalent to complex multiplication.
Yeah, you can actually kind of think of it. So if you had a circle of radius 5 on the plane, and then the places where the circle of radius 5 hits lattice points on the grid, those are the places where the knight can go, the normal knight.
Yes, but here we actually can do here. Let me show you what I mean by the multiplication.
Here it would be root 5, right?
Yes, but let me show you the what I mean by multiplication. So this is so assume the knight moves in. Say in this case it's 2 plus I. But this is a 2 and this is 1 and we call say this is I.
In the
So
complex plane.
yes. So then we say this is some K. So then this is a K, right? This is a minus Ki. This is a Ki minus K. So when we look at this lattice, we are really looking at all the multiples of K.
Right. Oh, yes. Yes. That's cool.
So that is why we get the symmetry of here. And in general, you can see because, well, if A and B are, if we have all multiples of A and B, A plus BI, we actually get that A squared plus B squared as how many knights are required.
Yeah. Mm-hmm.
Because we can see if we look at this line, they're just translated copies of each line if we look at respect to the knights.
Right, yeah. Mm-hmm.
So just need to look at multiplying it with A minus BI, which gets you the A squared plus B squared.
Mm-hmm.
But even though these aren't complex multiplication, they are quite symmetric. So if we look at all of these, we are having two different axes going to a point as what we are having, but they might differ a bit in terms of what is there. But since we can go either front or back, we can also look at these as instead of no, we can look at it as instead of complex numbers, we can also look at them as vectors. So we can also do the same thing here and all. We take this to be the origin, define this to be 0 comma 1, this to be 1, this to be 1 comma 0, or in the original one we also did this as 0 comma 1. So then we get a linear map. In fact,
Yeah, then you can draw the two axes.
yes. So we get these lines and then we get these are coordinate grids. But we get those also as extra lines and we get a coordinate grid, and on top of that we also can get A linear transformation.
Transformation of the original grid.
Yes. Then, because it's a linear transformation of the original grid, in fact, this number that we are getting is in fact the determinant of the linear transformation.
I see. Yeah. Mhm.
So in this case, if we say 2 minus 1, right, and minus 1, 2, I'm not sure if I'm getting this right. So yes, here we are getting 2 times 2 minus 1 times minus 1, which is 3.
So you're squaring this matrix, you're multiplying it with itself.
No, we are just taking the matrix of getting this because this is 2 then minus 1, this is 2 then minus 1, but in different ways. So then if we just take the matrix for the linear transformation and get the determinant of it, it is 3 in this case. And then in this case, it's 2 minus 1, 2, 1, right? So then it's 2 times
Yeah.
1 minus 2 times minus 1. And this is a special case. We get 2, 1, then minus 1, 2. Yeah. And then here we get 5. So
For this one, right? For the colored one.
yes.
And it also shows like whatever number you get, 1/n of that is the number which is filled up on the board.
Yes. Because if you think about it, there is no real ladder system for defining, oh, it's 1/5. Because
Yeah, it's intuitive.
yeah, because otherwise you would have to do something like take a square grid, take the fraction, and then make the square grid larger and larger. This is much more sensible and intuitive.
Mm-hmm.
So yes, if we can also take the complex multiplication as a linear transformation like this, and that is actually the same as spiral symmetry, but because we are rotating around the origin and then we're scaling. So, in fact, if we take the magnitude of the complex, no, it's not the, the absolute value of the complex number, and then the rotation, that is, we can characterize a complex number by the magnitude and direction as well.
Right. Mm-hmm. Yes.
So once we characterize complex numbers like this, we can also do a different form of multiplication because then we have something like this and we're scaling by r and r prime, and we're also rotating by theta then theta prime, which is theta plus theta prime. So then this is seems like a much simpler formula for complex multiplication.
Right.
So this is the polar form of a complex number when we actually consider its multiplication as a linear transformation, which is not just any linear transformation, but a spiral symmetry where where all the yes, the angles will be preserved in this, and the origin is preserved. It's not, and there are no reflections.
Right.
Mm, yeah, and there is also one more thing I would want to say, I guess, for results, which is there is an interesting thing about Gaussian integers, which is that, well, these are effectively ideals. Effectively, what that means is it's a lattice in this case. Because it's a 2D plane, it's a sublattice of it, where if you multiply anything in it by anything, it goes into that itself, which is what we saw here, right? This, and
Yeah.
yeah. So that is basically what is called an ideal. If we look at the integers, we have, we also just use, if two elements are in an ideal, then we just take the GCD we learned by Besut's lemma. That is also in the ideal. So it turns out if we look at integers, all ideals are just multiples of something. So,
Right. Yeah. Yeah, absolutely.
yes. In Gaussian integers, it turns out the same is true. But because we also have I in the mix, instead of looking like we would normally think of multiples of something as going in one line, because here we are having a two-dimensional thing which going to two dimensions.
Mm-hmm.
So you can, these are, so in fact, let me tell you something that, in fact, if we look at the Chinese remainder theorem in general, it has to be over ideals, and all these different knights are different starting positions, but effectively mod the ideal. Since you can go from one to the other by things in the ideal, just translating it from here to here to here to here.
Mm-hmm. Yeah. Yes.
So it's pretty much similar, and we don't notice it for just integers because the ideals behave just same as this, we would say. Yes, 1 mod 2 is the same as 3 mod 2 because their difference is a multiple of 2. So because of that, we notice the difference in integers or even Gaussian integers, but in other cases, we can take the more general case where it has to be over any ideals. It's pretty much the same statement.
Yeah. Yeah, it's pretty much the same thing.
Yes, I think this one, after if we continue after this, it would be too much for the session, even if there is a bit of extra time.
Okay, that sounds fair.
Yeah, yeah. Okay, so I think we'll end the session now. I'll stop